steps is manage to pick up a passenger and drop him off at destination without knowing that this is what's supposed to happen or getting any.
That's right. But you can see how it explores. And now that's the lead into the next video. So the last task that we used was more meaningful to some of us than others. But this is a video game from, we'll call it my childhood, most of my childhood, called Pitfall. It was on the Atari system. Little guy has to get off the screen. He actually has to do he has to get off a lot of screens and collect a lot of stuff. But just for the first screen, we're just trying to get over there. We have an emulator for the Atari system. We plugged our reinforcement learner into that. So the input to the system was the bitmap of the screen, and the output was the joystick commands. Now we're doing reinforcement learning. So that was a little bit, to solve the vision problem in this case, what we did is we recognized solid blobs of colors. This was old graphics, right? So this peach color is exactly the same as this peach color, and it's only in this part of the screen because it's all driven off the sprites. So it wasn't so hard for us to write a little piece of code that just grabbed little rectangles. Like this tree bark is a possible object, and it's in this position, and this height and width. This, I don't know what it is, but it's sort of coherent. We'll call that an object. We'll call this an object. We'll call this an object. So it just, from the screenshot, generates a list of objects. And what it now wants to know is, for each action that I take, how will the attributes of those objects change? Just like in the taxi problem. It doesn't know that this is us, or that it looks human or anything like that. It just knows it's one of the objects, and then it starts experimenting. It tries the right action and the left action. But built into this, and one of the reasons we can get the fast exploration, is it assumes that all of the things being equal, all that matters is how objects have touched each other. Right? There can't be, as far as it knows, any kind of magic thing where it's in the middle of space and actions work differently here than here. It assumes that the only reason something could act differently is, well, now I'm touching this object where I wasn't before. So you can see that what it does when we set this running is it first takes a couple actions, and then it understands what they do, and now it reaches the pit, and it starts trying everything it can do with respect to the pit. And then it gets it, and then it tries the same thing on the ladder, where it's up, down, jump, left and right. And then it knows the ladder, but it doesn't know what happens if I'm on the ladder and the ground. So it tries things out there. All right, I get that. Oh, what's this thing over here? Let me bump up against it a little bit. Oh, well, that didn't do anything. Okay, well, that looks like I'm not going past it. So it knows it's trying to get off the screen to the right. But there's still an object that it hasn't interacted with yet. Well, a little bit more on the pit. And now the log, so it briskly rubs up against the log. It's losing points while it's doing this, but it doesn't care. It's enjoying learning about the log. It falls off the end of the screen, but now there's nothing that it doesn't know. And so the second trial, it gets to the pit. It jumps over the pit because there's nothing good down there. It jumps over the log because it loses points. It gets to the end. And the undergrad who actually did the hacking to connect things up made it do a happy dance at the end. So that's not actually part of the game. I appreciate the sentiment. All right, I saw a hand go up, I thought? No? Okay. So that was the main bit there. Tomorrow I'm going to talk in the machine learning seminar, and I'm going to talk about how we're getting away from these worst case assumptions in a hypothesis class and adding Bayesian priors on top of things. And we can get hack MVP-like guarantees, but in a setting where you have some prior knowledge about the probabilities that some worlds are more likely than others. We're working on, the other thing that's a big problem for us now is we can now quick learn very big, complicated state spaces, so big and complicated that we don't know how to act in them because they're too big. So we're working on the planning part of this to make that more efficient, especially with Monte Carlo planning. And then here's the last little cartoon just to end things up. We just assumed that exploration is a good thing, but I saw this cartoon and made me realize maybe it's not so much. So here's a person finds a lever in the middle of nowhere, he's never seen it before, he pulls it, and he gets hit by lightning. So now there's two kinds, now this is perfectly reasonable so far, but the cartoonist says there's two kinds of people in the world. A normal person would conclude at this point, I guess I shouldn't do that. Scientists, on the other hand, is like, I wonder if that happens every time. So our algorithms are definitely in this class. They really want to know if that happened every time. But the Bayesian algorithms are maybe a little bit more on this side. But that's the way I think I am as a person, and that seems to be how my algorithms are turning out as well. So that was my pitch.
Thank you. We had quite a lot of fun.